Hello, everyone, and thank you for attending this virtual special session on model-based deep learning. My name is Hassan Mansour. I'm a senior principal research scientist at Mitsubishi Electric Research Labs. Today's talk will be dealing with learning plug-and-play Proximal Quasi-Newton Denoisers. This is joint work with Abdullah Al-Shabili from New York University. Abdullah was an intern at MERL during the summer of 2018 when we conducted this work. And this is also in collaboration with my colleague, Petros Boufounos from MERL. And today's problem deals with developing algorithmic solutions for general inverse problems. Now, inverse problems are ubiquitous in a variety of signal processing applications. Of these, I'm going to mention, for example, inverse scattering, which is the task of estimating the scattering potential of an object by observing the scattered wave fields that are measured as sensors outside of that object. Another application is the radar imaging problem, where the task is to determine the position of a strong reflector and also potentially determine the shape of that reflector by transmitting electromagnetic waves or radar waves and then receiving the reflections back at a receiver. And yet another application would be airflow or dynamical system sensing, where the task there is to try to estimate the dynamical system parameters and the flow parameters by only placing measurements that are on the periphery of a room in which that flow is moving. And from those peripheral measurements, we want to be able to determine the entire flow inside the volume of the room. Now, to formalize the problem, we consider the task of observing measurements y of some signal x star through the forward or measurement operator a, so that y is equal to a of x star plus e. And as an example, we can consider x star to be just an image, for example, and the operator a to be the camera transfer function, which also includes some blurring functionality and additional noise. So the measured image y is a little bit blurry, or in fact, it's a blurry version of the signal a of the signal x, and it also has additive noise, which is the vector e. Now, one of the most effective approaches for solving such problems has been to set up an optimization problem where we want to minimize over the image x, and what we want to minimize is the function f of x plus some regularization parameter lambda times a penalty function rho of x. And here, f of x quantifies the mismatch between the measurements and intermediate estimates of x as observed through a, whereas rho penalizes solutions that differ or that are far away from the prior structure that we think x should have. In order to solve such optimization problems, proximal methods have been very effective and computationally efficient. Specifically when the functions f and rho are proper closed convex, and when f is differentiable, then we can use the proximal gradient descent method, which is a first order method, that iteratively finds x star by following or by using the update equations, where you have estimated an intermediate variable z, which is equal to xt minus alpha times the gradient of f. So that's a standard gradient descent step. And then, or that's called the forward step. And then the backward step is you apply the proximal mapping operator with respect to alpha lambda rho to the signal z. And the proximal mapping operator is primarily an operator that solves the problem argmin of x of x minus z. So it finds the closest point to z that obeys the structure that's defined by rho of x. Now, when f is twice differentiable and it has a Hessian that is invertible, in that case, a more efficient method would be to use the proximal Newton method, where in this case, z is computed by taking x, and you subtract from that h inverse multiplied by the gradient of f. And of course, this would be useful in the cases where it's easy to compute h and its inverse. However, if the computation of h inverse is computationally difficult, then there's really there wouldn't be a good benefit or a big benefit in using these approaches. One of the critical tasks, though, in using proximal Newton methods is that instead of having a proximal operator, which minimizes the Euclidean distance between x minus z. In the case of proximal Newton methods, the distance is computed between x and z is computed with respect to the matrix H, which makes it a little bit more challenging, basically, to compute these proximal mappings. Now, an approximation for these proximal Newton methods are called proximal Quasi-Newton methods, where H inverse could be replaced with, more often than not, diagonal approximation. And in this case, the proximal mapping operation itself, when H tilde is actually diagonal, becomes much more amenable to computation. It's easier to compute. Now, when you look at the proximal operator itself, or the action.proximal operator, we see that it corresponds exactly to the maximum a posteriori estimator of a signal z, which is primarily x plus some white Gaussian noise. So what that indicates, it makes us think that, well, the proximal mapping in this case is acting like a Gaussian denoiser of the signal x. So that has led people in the past to, not too far past, but that has led people to propose works or algorithms that replace the proximal mapping with sophisticated or data-driven trained Gaussian denoisers. And among those works, I would mention the plug-and-play method, plug-and-play priors, the denoising approximate message passing, and the regularization by denoising. So PnP, DAMP, and RED. In this paper, we're going to, or in this presentation, we're going to focus mostly on the plug-and-play approach. I would just want to add that also there have been extensions for these techniques where they unfold the iterations of the PGD, or the proximal gradient descent, over, let's say, t iterations, and then they try to train a denoiser that's suited for that specific type of inverse problem that's being solved. Now, when we compare the structure of unfolded algorithms to plug-and-play denoising, what we notice is that let's consider first the case where a is linear. So a of x is actually equal to a times x, and we assume that f of x is the Euclidean distance between y and ax. In this case, we can write z as identity minus alpha times a transpose a times x, plus some alpha a transpose y, and then we apply the proximal mapping to that z. But now if you replace the proximal mapping with a denoiser and start to think about that whole algorithm as a layered neural network, what we see is that every iteration of this optimization problem is actually corresponds to a layer in a deep neural network. So if we unfold the iterations into big T unfold the algorithm into big T iterations, then that would correspond to T layers of a deep neural network. Now, when we compare the unfolded algorithms training to plug-and-play approaches, or the regularization by denoising, or RED approaches, one of the benefits or advantages to PnP and RED is that by training single denoiser, they can be adapted to a variety of inverse problems where A can have a different structure, so long as we're observing the same type of signals X. Whereas with the unfolded training of algorithms like Lista, for example, the training itself forces you to be stuck to a specific type of forward operator. One disadvantage to the current implementations of plug-and-play methods is that there is no proper ability to assign a noise level to the denoiser that is different from what has been used in the training data set. Now, very recently, there was an approach, or there was a paper that proposed denoiser scaling that could remedy this problem for certain types of denoisers. However, it was still unclear how to choose that the best denoising parameter. In our paper, we tried to go through a different route where we looked for denoisers that take in as input a noise level map. And what we found was we found the FFDNet denoiser, which takes a noisy image as input, partitions it into 4 sub-images by taking, let's say, every 2 by 2 pixels and then assigning them to a different channel. And then it also takes a 5th channel, which is the noise level map. And what we see is that using the 5 different channels, the network processes this data to output a denoised set of sub-images, which are 4 channels of denoised sub-images, which are then combined together to produce the high-resolution image. Now, when we consider the setup, this actually resembles more the proximal quasi-Newton approach, where the denoiser of that's being used, so the denoiser applied to Z, in this case, takes as input alpha, lambda, h tilde. And specifically when h tilde is a diagonal operator, then you can see that assigning the noise level map corresponds to specifying the parameters in that h tilde. So given all of that, what we propose to do is basically incorporate a new module into this, a new train module into this overall denoiser, which is what we call the noise level estimator module. Now that is primarily composed of 2 small convolutional layers with 24 filters each and 3x3 of size 3x3, and with the ReLU activations. So what that does is, given the noisy image as input, the noise level estimator computes or estimates the amount of noise that should be applied spatially to the image. And then that is taken into the input of the FFDNet denoiser. Now, in order to train such a model, what we do is we unfold the proximal quasi-Newton iterations. And in this case, we actually drop the H inverse from the estimates of Z, or the computation of Z. And that's because we found that it was, the training was numerically unstable because we're computing element-wise inverses in the training. So we dropped that part, but then we kept the diagonal scaling in the proximal operator, specifically in the denoiser. And we unfolded the iterations into T iterations, and then we only used a small training data set to compute the noise estimator parameters, which are tied over all T iterations. So just to give you a quick idea of what were the training and evaluation settings, basically we used the pre-trained FFDNet denoiser. As I mentioned, we unfolded over 10 iterations, and then in addition to computing the parameters of the mini CNN for the noise estimator network, we also fine-tuned the last 3 layers of FFDNet. The training data set was 100,000 patches from the Waterloo exploration data set, and we also applied motion blur. Basically, we targeted a deblurring application in our setup. We applied the motion blur, which was generated by sampling 6 angles between 0 and pi, and then each blur kernel has a different length between 5 and 15 pixels. We compared with the BM3D plug-and-play algorithm with standard PGD PNP, basically where we use only the FFDNet denoiser as it is, and then with another version that fine-tunes the last 3 layers of FFDNet. And we also took one single iteration of our PQNM, so that's our proposed approach, and we trained it end-to-end to take as input a blurry image and output a completely deblurred image, as opposed to the other framework where we use a denoiser and then use the unfolded structure in order to achieve the deblurring. Just with respect to the last part, the training used the same number of parameters that were used to train the PQNM PNP. We used on the same training data set, and the purpose of it is to highlight the benefit of the plug-and-play approach. When we look at the numerical results, we can see that our proposed method, so that's the last column, achieves anywhere between 1 and 3 dB improvement over all other methods, specifically over the end-to-end trained network, over the PGD with the fine-tuning and the standard PGD, and also over the BM3D denoiser. And just to see some subjective results, you can see that you can look at the last column compared to the other ones. The last column definitely shows that it has crisper and sharper images than the other ones. This is for the one example with the girl, another one with the butterfly, and again, you can see the edges are much sharper in the last image compared to the other ones, and same thing with the bird. So to wrap up, we emphasize that integrating trained denoisers in a plug-and-play approach has shown promising state-of-the-art results. However, there are still issues that need to be addressed. That's specifically with respect to choosing the denoising level. And our proposed approach essentially solves this specific problem by incorporating another mini CNN into the denoiser and training it with in an unfolded structure. And with that, I want to thank you all for watching, and I just want to wish everybody to stay safe and healthy, and have a good day.